We present DartControl, a diffusion-based autoregressive motion model for real-time text-driven motion control. Synthesizing realistic human motions has numerous applications, such as in gaming, augmented and virtual reality, and generating synthetic data for scenarios where collecting real data is either costly or poses privacy and security issues. Text-conditioned motion generation methods have gained popularity for their intuitive and user-friendly language interfaces. However, current text-to-motion methods face notable limitations that hinder their practical utility. Firstly, these methods primarily generate isolated, short motion sequences in an offline setting, whereas real human motions are inherently continuous and occur in real time. Secondly, they lack effective control mechanisms to achieve spatial goals while ensuring adherence to the text semantics. To address these limitations, we introduce Dart, a generative motion model capable of online motion generation from text prompts. Additionally, Dart provides a general framework for diverse motion generation tasks that involve spatial constraints. We formulate online text-to-motion as an autoregressive generation task. Given an initial motion seed and a stream of text prompts, the goal is to produce natural motion sequences that align with the text semantics while ensuring smooth transitions. Designed for efficient online generation, Dart employs an autoregressive motion primitive representation. This representation models infinitely long motion sequences as a series of overlapping motion primitives, with each primitive containing H history frames that overlap with the previous primitive and F future frames. Each frame of the motion primitives is represented using an over-parameterized representation based on the simple X parametric body model, including joint rotations compatible with animation pipelines, joint locations that form the basis for further spatial control tasks, and the first-order temporal differences of the location and rotation features. Building on the motion primitive representation, we introduce Dart, a latent diffusion-based autoregressive model for online text-to-motion generation. Dart consists of a variational encoder that compress motion primitives into a compact latent space, and a latent denoiser model that iteratively generates motion primitives conditioned on text prompts in the learned latent space. Dart first learns a compact latent space for motion primitive through variational learning. The encoder network compresses future motions into a latent variable, conditioned on the history motions, while the decoder reconstructs the future motions based on the history motions and the latent variable. This compression results in a more efficient latent space for motion control and reduces artifacts like jittering, enhancing the quality of generated motions. Building on the learned latent motion primitive space, Dart trains a latent diffusion denoiser to iteratively generate motion primitives conditioned on the text prompts and history motions. The latent denoiser is trained with the simple objective of directly predicting the clean variable z0. With only 10 diffusion steps, the simplicity of the motion primitives and the compact latent representation enables efficient online generation of natural human motions. Using the trained denoiser and decoder models, Dart can autoregressively generate motion sequences in response to streams of text prompts. We demonstrate how Dart enables real-time text-driven motion synthesis in this command line demo. We present qualitative comparisons of Dart and baseline methods for the task of text-conditioned temporal motion composition. Dart generates high-quality motion sequences with smooth action transitions and accurate semantic alignment to the text prompts, outperforming baseline methods. While language provides a human-friendly interface for controlling motion semantics, relying solely on text can be insufficient for precise spatial control, such as when teaching dance performances or describing specific spatial details like the hole in the wall. To address this limitation, we propose a general framework for motion generation with spatial control leveraging the trained generative DART model. We formulate motion generation with spatial control as a constrained optimization problem. Given the task-specific spatial goal, the objective is to generate a motion sequence that approaches the goal as closely as possible, while adhering to scene context and physical plausibility constraints. However, directly solving the motion control task in the raw motion space often leads to unrealistic motions, as most samples in the raw motion space do not represent reasonable motions. To enhance the generated motion quality, it is advantageous to constrain the solutions within a manifold of plausible human motions. DART offers such a latent space of plausible human motion skills, where each latent noise ZT can be transformed to a short, realistic motion primitive. Therefore, we reformulate the motion control problem as a latent space control problem to achieve more realistic generated motions. We propose two methods for solving this latent space control problem. The first straightforward solution is to use gradient descent optimization over the latent noise variables to find the optimal solutions. This optimization-based solution is plug-and-play, enabling diverse spatial control tasks such as keyframe body or joint-based control, as shown in the following video results. In the text-conditioned motion in-between task, our method generates high-quality motion sequences that accurately achieve the goal keyframe body while maintaining alignment with the text prompt semantics, outperforming baseline methods. Furthermore, we show that scene context can be integrated into our optimization-based control framework to synthesize human-scene interactions. In addition to optimization-based control, we propose a reinforcement learning solution for efficient online generation. We model motion control as a Markov decision process with a latent action space from DART and use RL to learn policies for goal achievement. At each decision step, the policy observes the text prompt, history motion, spatial goal, and surrounding environment to predict the latent action that guides the human toward the spatial goals. The predicted latent action is decoded to motion frames using the pre-trained DART model, and then canonicalized to update the motion history for the next decision step. We reformulate the motion control optimization problem as a reward maximization task, training the policy to maximize rewards that encourage achieving the goals while adhering to scene constraints. We apply RL-based control to the text-conditioned goal-reaching task, where the human must reach dynamically updating waypoints using prompted locomotion skills. Our trained policy model efficiently controls humans to reach these waypoints while adhering to text semantics, achieving a generation speed of around 240 frames per second. Our method can be integrated with the physically simulated motion tracking methods to generate more physically plausible motions, such as improving joint floor contact and eliminating scene penetration artifacts. Our optimization-based control approach can effectively manage both dense and sparse joint trajectory control. When trained on coarse, sequence-level text labels and tested with prompts describing multiple actions in one sentence, the model generates random transitions, ignoring specified orders. This occurs due to the semantic ambiguity of using global prompts to guide the generation of short, local motion primitives, resulting in unpredictable transitions as long as they are locally feasible. However, by explicitly decomposing the sentence prompt into a sequence of individual action prompts, our method can generate motions adhering to the intended action order. This decomposition can be achieved by utilizing common sense reasoning in language models like GPT-4. Our method can stably generate minutes-long rollouts of inherently extendable actions, such as a person jogging in circles, performing cartwheels, and dancing. On the other hand, some actions have boundary states marking their completion, leading to fluctuations if extrapolated beyond this point. For example, kneel down reaches completion when the knees touch the floor. Further extrapolation is not represented in the dataset and is not naturally anticipated, causing fluctuations if the rollout continues with the kneel down prompt. Thanks for watching.